headwaters of the Santa Clara River, Ventura County, Southern California. A river system which, like most river systems in this region, is intensively studied and continuously monitored. Even in the most remote mountain areas, automatic monitoring stations have been established. And this is the Santa Clara River itself, now at the end of the long dry summer, little more than a trickle, and certainly hardly seeming to merit so much interest. But in the winter, the need for monitoring becomes more apparent. For flooding is a serious threat. Winter rains are heavy and intense, and they produce dramatic increases in stream discharge. The need for early flood warning is obvious. We're going to look at the way in which data is collected and how it's processed to give early warning. For this, a mathematical model has been constructed in the computer at the Flood Control Center. This is based on the standard hydrological model. Rain falls on the ground surface of a catchment like the Santa Clara. Some of it flows down the slopes towards a river channel. This is overland flow. Most of the water in the channel will eventually reach a lake or the ocean. Rainwater also soaks into the soil profile. Some of this will escape into the river channels. The rest will percolate into the zone of saturation below. From here, it will escape only slowly into rivers, lakes, and seas. Finally, some of the water will be lost into the atmosphere by evaporation and transpiration through plants. Each of these inputs and outputs varies, and the changes are reflected in the flood hydrograph, the response of the catchment to any storm event. The input is, of course, the rainfall. This is measured here using a standard American rain gauge, 8 inches in diameter, which gives the total rainfall over a known period. Alongside, a continuous record is kept on this rain gauge. The pen is activated by the weight of rain collected in the instrument, and the chart gives both the period and the intensity of the rainfall. Here, for example, it indicates one short period of rainfall in the last 24 hours. The main output in the catchment is the water flowing in the river channels. This is best measured using a flume. Let's look at this small flume, used to monitor water passing through an irrigation system. The water is funneled into the flume, where it passes through a known cross-section. By measuring the depth of the water at this point, the discharge through the flume can be calculated. On this chart, the water depth, or head, is given, and the discharge can be read off. On the rivers and creeks in the Santa Clara Basin, large flumes have been constructed. These are concrete channels of known cross-section. The water passing through the flume enters a stilling well behind this metal grill. In the well at the top, there is a gas bottle from which gas is released through a small tube at a known pressure. The influx of water causes a change in gas pressure. This can be measured and used to calculate water depth. The reading is given on this chart. Here, it is obviously 0. Water loss by evaporation is also measured, here using an evaporation pan. The level of the water in the pan is known, and any change in level can be measured when the site is visited. In this case, a needle is raised through the water until it just breaks the surface, here on the left, and the level of the needle, and thus the level of the water surface, is read on this scale. This gives the evaporation which would take place from a water surface. It is the potential evaporation. Actual evaporation is calculated from readings of wind, temperature and relative humidity, which are recorded at the same site. In this instrument, it is a hygrometer. The top line represents temperature, the bottom relative humidity. In the remote mountain areas, the instruments are similar, but they are automatic and can be read from the central control room. This, for example, is a rain gauge. It is mounted on a column which also carries an aerial. The instrument uses a tipping bucket mechanism. We'll see this method in operation later. And each tip, containing a known amount of rainfall, is recorded and transmitted back to a central control room. And this stream is monitored by an automatic gauging station. Water is taken in through an inlet in the riverbed. It flows into a stilling well under the gauging station, and the water level is read here by a system of floats. The data is stored on punch tape. There is a landline to the control room, and the data can be accessed by telephone. When rain begins to fall, this is the first storm of the autumn, the system can be used to monitor both the scale and intensity. Data is summoned from the automatic stations. Rainfall readings are displayed. And they suggest that the storm is local in extent and is unlikely to cause any increased discharge in the streams. And when the automatic gauging station in the area of rainfall is accessed, there has been no significant increase in discharge. In February 1980, the situation was very different. In places, rainfall exceeded 5 inches in 24 hours, and the bulk of this fell within the space of 6 hours. This was the culmination of a period of wet weather, and the predicted discharge of about 50,000 cubic feet per second suggested that serious flooding was possible. And the predicted response of the Santa Clara River was equally alarming. After a delay of about 8 hours, catchments in this area are usually dry and can absorb a great deal of rainfall. Discharge in the streams would then increase, and the rise would be both swift and steep. Within hours, the effects could be seen. Water was already lying on the floodplain, indicating that the ground was by then saturated. And in the rivers, water levels were dangerously high. Further rain, and the waters continued to rise. Large areas of floodplain were by now underwater, and flood damage was widespread. This was the fate of the railway bridge we've just seen. But the full extent of the damage only became apparent as the flood subsided. River channels had been changed out of all recognition. banks had been cut back and erosion had taken place on a massive scale. Entire hillsides had been undermined and had slipped down towards the river. The channels, clogged by this influx of debris from banks and valleyside, became braided, and vast sandbanks appeared. In places, tiny creeks had been gouged out to form minor rivers. River channels had been enormously enlarged. Here, for example, the bridge over the river withstood the flood. The approach roads on either side were washed away. In the face of devastation on this scale, the need for monitoring and early warning is obvious. But what about the rivers here on the slopes of Plynlimmon in mid-Wales? The catchments here are even more intensively studied, and flood control is not the main concern. These are the headwaters of the River Wye, a moorland catchment covered by rough grassland. And this, less than 4 kilometers away, is the source of the River Severn, the longest river in Britain. It rises on the summit of Plynlimmon, and the catchment is again moorland. But only 1 kilometer downstream, and the vegetation is very different. The entire valley is now a coniferous plantation. We're going to look at the effect of vegetation on the discharge of these two rivers, one flowing in a grassland catchment, the other in a forest. For this, detailed and accurate measurements are needed. Rainfall is measured at a large number of points in the two catchments, and a range of instruments is used. This is a standard British rain gauge, a 4.5-inch funnel and a glass collecting jar. The contents are measured in a specially graduated cylinder. Because this type of gauge protrudes into the air, there can be considerable turbulence around the aperture. Most gauges here are located in pits. This reduces turbulence, and the plastic mesh prevents rain bouncing back into the gauge. Results here at Plynlimmon suggest that readings in these gauges are up to 8% higher than in the standard gauge. Methods of recording also vary. This is a tipping bucket gauge. Rain falling into the aperture of the instrument is funneled into one of these buckets. It tips when a known weight of rainwater has collected. In this instrument, the data is stored in a small computer, and rainfall figures can be retrieved for any day in the month. Large flumes are used to measure discharge in the rivers. As in Ventura, the river is funneled through a channel of known cross-section. This means that by measuring water depth alone, discharge can be calculated. Baffles dissipate the energy of the river and reduce turbulence. This gives a smooth surface for measurement. In some cases, measurement is carried out in a stilling well alongside the flume. A system of floats being used to create a continuous record of changes in water level. This data is stored in a variety of ways. On cassette, for example, or in a central computer which is accessed by means of satellite transmissions. Rainfall on two catchments so close together is obviously very similar. Discharge in the streams is strikingly different. This is the response of the Wye to a storm event. The flood hydrograph rises quickly and peaks at 92 cubic meters per second. The response of the Severn is less dramatic. It is delayed, the peak is much lower, and the decline is less rapid. What causes this difference? The underlying rock is the same, the catchment area is similar, and rainfall is virtually identical. Only the vegetation is different, and this suggests that the planting of forest in the Severn catchment has slowed down and reduced the movement of rainfall into the streams. Let's examine this in the field. The rain falling on the forest is measured using canopy rain gauges like this. The instrument is mounted on a tower, but readings can be taken at ground level in the way we have already seen. At the same time, the amount of rainfall actually reaching the forest floor can also be measured. The rain flowing down the branches and the stems of the trees is channeled into containers, and any water dripping from the canopy is collected. The amount of water reaching the forest floor is much less than the amount of rain falling on the canopy. And this difference is largely the result of evaporation. Water is also taken up through the roots of the plants, and some of this returns to the atmosphere as a result of transpiration. The total loss resulting from evaporation and transpiration, it's called evapotranspiration, can be measured using a lysimeter. This is a small lysimeter, an oil drum sunk into the ground. The surface area and the volume of soil is known, and the moisture content is maintained at saturation level by adding water each day. The rainfall is continuously monitored, and any water passing through the lysimeter is collected at the base of the instrument. This is measured, and the difference between the input of water and this output is the loss by evapotranspiration. At Plinlimmon, the lysimeters are much larger. We can see their outline here. Plastic sheets are placed under large areas of land to form collecting areas. The boundaries are clearly marked by these fences. Rain falling on the area is measured, and the water flowing from each lysimeter flows along these pipes. The amount is recorded by means of a tipping bucket system. Each bucket will tip when a known amount of water has entered it. Total evapotranspiration can then be calculated. Evapotranspiration and the interception of rainfall is greater in a forested catchment like the Severn. This, more than anything else, explains the different responses of the two catchments, the reduced flow in the Severn and its more gentle flood hydrograph. Such changes are significant if rivers are to remain an important source of water supply, and afforestation in upland areas like this must be monitored to ensure that a balance is maintained.
If you could just sort of say, Nash, or your heck, in such and such a town there is a certain one, Owen Bowens. Oh, please, sir, if you could just say that, sir, one Owen Bowens.
Very well.
I'm very sorry to have troubled you with my humble presence, sir.
I'm sorry to have troubled you with my humble presence, sir.
It's perfectly all right, gentlemen. Glad to meet you.
He's quite a nice fellow, really. He's not
I think there's an awful lot of civil servants in this town. And it does strike me that they've mistaken me for somebody of great importance in the government. I must have spun them a fine yarn at lunch today, eh? Fools. I think I'm going to write to